Good morning. Can we start? 45 minutes organic chemistry, but very important 45 minutes. You will learn today a concept I guarantee you will be able to use and to apply all your life in organic chemistry, which could be the next 40 years, could be also only the next 2 years, right? Who knows? So let's go back to the problem, or to the question I posed last time. And that is the reactivity of cyanide, which is a reasonable nucleophile, with alkyl halides, which are good electrophiles in nucleophilic substitutions. And this can in principle lead to two different products. To the class of compounds of nitriles, and to isonitriles. And the interesting factor is that it very much depends on the cyanide source. If you use sodium cyanide or silver cyanide, which one you will get. So obviously, the interaction of the nucleophile with the substrate can be different depending what kind of maybe countercation is, or you will see in the moment the explanation I favor here how the electrophile can be varied. But let me go one step further here. So this is the cyanide. But let's look at a different nucleophile here first. And these are Grignard compounds. And so my question is, the Grignard compound is also very strongly polarized carbanion type alkyl group. So there could be a nucleophilic substitution along these lines. You know that this reaction normally does not happen. Why do you know this? You must know this. Everyone knows this. Who knows how you synthesize Grignard reagents? Does anyone remember from second year lecture Grignard reagents? You synthesize from an alkyl halide by reacting it with magnesium. Now, if the Grignard reagent would react with alkyl halides, the moment this would form, it would consume its precursor. So apparently this is not working. This does not really happening. And it happens in more specific examples, but in general it does not. On the other hand, if you look at other substrates like carbonyl compounds, let's take an ester. A Grignard reagent will very rapidly add to the carbonyl compound. It will form an intermediate first, and we will go into carbonyl compounds and its reactions more in detail, and then eventually it will react further. whatever the products are here. But at the same time, if you look at cyanide, let me put this again here. If you take an ester and you try to react it with sodium cyanide, nothing really will happen. So interesting, the nucleophile in one case reacts with an electrophile, and another nucleophile does not react with this electrophile, but it reacts with an electrophile. The first nucleophile is not reacting. If you would simply think about strength arguments, that seemed to be unlogical, right? Because the stronger nucleophile of both should react with either of our electrophiles. And so that somehow, at least at a first glance, really does not make too much sense. So let's go back one step and discuss strengths of nucleophiles with respect to basicity, because a very good estimate for the strength of the nucleophile is how basic, how strong the base is. So as a rule of thumb, and it's really just a rule of thumb here, it's the stronger base is the stronger nucleophile. And this holds pretty much true, with the only thing to consider here, that some of the bases are sterically so big that they cannot react as a nucleophile because they cannot reach the interior of your substrate. It will react as a base because the hydrogens are more on the outside of an organic molecule. If you do a nucleophilic substitution, you're attacking a carbon center, and you have to go more to the interior of your substrate. So here, as the more or less exception, big bases are not good nucleophiles. Simply because they cannot reach the reaction center. Okay, this of course means directly the stronger the base, the stronger the nucleophile. It also means the weaker the conjugated base, the conjugated acid, so here, if you go from the stronger the base, the stronger the nucleophile. So here we're considering the nucleophile, respectively the base. And then you can also say the weaker the conjugated acid. So here we are looking now at the acid. The stronger the nucleophile. Again, Because if you have a weak acid, then of course if you deprotonate it, you have, on the other hand, a strong base. The reason I would like to look at the acid is that the acid values, the so-called pKs values, you find them in any book in terms of tables. So this represents acid strength. And again, you don't need religiously to memorize pKs values, but again, you should have the idea of a certain range. And so let's look at a few. Where we typically stand. So let's take an alkane, take an amine, carbonyl compounds like an ester, aldehyde, let's go over here, water or alcohols, phenols. Since we are going to look at cyanide in a moment, we are looking also at HCN. And then let's take something like carboxylic acid. So in what kind of range do we operate? The numbers we have to go here. You see I have already put like the weakest acid and the strongest acid if we just talk about organic compounds. So here weak, strong, stronger, strongest. So anyone knows any pKs value from any of these compounds which are on the board? Just to calibrate us. Are we dealing with a range between 0 and 1,000 or 0 and 100, or what do we have to be able to operate in? So acetic acid has a pKs value of 4.75. That's right. So carboxylic acids, rule of thumb, are in the area of 0 to 5. Depends then also on substituents. So you said acetic acid, this is more on the higher side, around 5. If you go to trichloroacetic acid, you go more to 0. Okay, so that's a good benchmark. Where are we on the other hand here? Does anyone know? Yeah? How much? 35. It's a lot higher. So here we are around 50. And it depends on the source in which book you read this, and it also depends where it is measured, because obviously you cannot measure this in water any longer, because water would readily do the acid-base reaction, and so you have to go out of water. Acetic acid you can measure in water. Everything which is a weaker acid than water has to be measured in a different solvent. So typically, pKs scales of organic compounds are all measured in DMSO. But as I say, it's not so easy to say this, but rule of thumb is pretty okay. So huge range, right? You go from a carboxylic acid 0 to 50 here, so 10 to the power of 50. That's really an extremely high range. Amines, here we are around what you suggested, maybe something around 35. Again, depends also a little bit on the substituents here. Esters might be in the range of 25 to 30. Other carbonyl compounds maybe around 20. You see this goes somehow in 5 steps. Water, where's water? Everyone should know this. Even if you don't know this, you should be able to calculate it. Yeah? 14 is a little bit too strong. Why did you say 14? That's right. You said I know water has a pH value of 7. So you say 10 to the minus 7. 10 to the minus 7 is 14. But you then divide through the liter, through the 55 moles of water you have in there. So it's around 16. So here we are around 16. Phenol is around 10. Cyanide, around 9. So more or less, you should have a handle on the general range of these substrate classes. And I don't care if you say, oh, I read acetic acid has a pKa of 26 or 28 or 22 or 23, but you should have the range around. And then you should also, and that's something we will do progressively as well, you should also be able to argue this. You should be able to argue to say, why is this proton on an ester less acidic than the proton, the alpha proton, on an aldehyde here? So let me stress again that this is the pKs value which we look at. So now if we compare cyanide, so cyanide is the acid is a much stronger acid. So the conjugated base is a relatively very weak nucleophile. If you compare this to the nucleophile which would be behind this here, this is our Grignard reagent. So here you have the deprotonated methane. So the base strength here should be, or the conjugated base here should be around 40 orders of magnitude. Think about this. In the moment we talk about saving Greece, here we're talking billions, right? 10 to the power of 9. Here we are talking 10 to the power of 40 in the differences. So it's absolutely huge. So this is a 10 to the power of 40 stronger base than cyanide. Let's put this here. Sodium cyanide would be. And nevertheless, cyanide reacts in a nucleophilic substitution readily with alkyl halides. Grignard reagents do not. Cyanide does not react with esters. Grignard reagents do. So there must be something more than just nucleophilic strength based on basicity, and even with the argument of steric encumbrance, no matter how small you make the nucleophile, it will not readily react with an alkyl halide. Okay, so interesting what is going on here. And the way to get a handle on this, a concept was proposed, and this is as important and general rule as what we said, there are steric and electronics for everything. This has to do with electronics. It's the SIB principle, the principle of hard, soft, acid, base. And what it does is it classifies acids and bases not by the strength measured based on the pKa. what it does is it measured it by something you have to define, by something hard and soft. And as the general rule is here, that hard-hard combinations are good, soft-soft is good, but hard-soft combination is not good. And so reactions where you try to combine a hard acid and a soft base, whatever that means, hard and soft, this is not a good combination. And so now we need to define hard and softness of compounds. And the definitions, and again this comes from experimental evidence, of course, the definition for hard is that these are small, charged, and non-polarizable acids or bases, and typically soft is big, neutral, and you can easily polarize it. So let's fill this a little bit with life. Shouldn't this go up? Oh, okay. So then if we try to fill this with life, if we would start with hard acids and hard bases, what would you think is then, according to this definition, that a entity which is small, charged, non-polarizable, this means it keeps the electrons close to each other. This goes pretty much together with being small, right? Because then you cannot polarize the electrons around. What would you think is the hardest, or one of the hardest things then? Sorry? Fluoride. Base or acid? Sorry? Why is fluoride an acid? An acid is the fluoride is a base, right? Because the fluoride is negatively charged, and it would try to react with protons. The acid is the other way around. So fluoride would be clearly in the base part, but indeed this would be extremely hard. It's very electronegative. It does not want to share any type of electrons. It's small. It's charged. So on the acid side, what do we think then is the hardest acid or particle you can think of? Proton, right? Nothing. It cannot get smaller. In fact, the proton is so small, as you all know, and our inorganic colleagues will tell you that at least in water, proton is never really a free entity. It is usually protonated to something like water, H3O+. But of course, again, the same idea. It doesn't even have any electrons to polarize, so that's extremely hard. Let's put here, on the other hand, let's put some soft things here also. Soft, acid, soft base. let's stick with the halides. How do you think this will change? You go from fluoride to chloride to bromide to iodide. Which direction will this go? Will it become harder or softer? Huh? Softer. Why is this? It becomes bigger all the time. All right. Iodide is not very it's much less electronegative. It's very big. Can easily be polarized. Right. So again, this is a sliding scale. But maybe I would still put the chloride here and then bromide, iodide maybe here. But keep in mind, this is not an absolute scale. Usually you always will compare two entities. But the general prediction that fluoride, that the halides become softer from fluoride to iodide is clearly true. Any type of soft acids? No? Or you want something else? Hydride. H minus. So the proposal here is hydride. Its charge is, he said, the answer from the audience was it's relatively small, but it still has a lot of electrons around. And then it should be a hard what? Or what is the proposal? A base, right. So the question is hydride. Where do we put in hydride? Is it, and again, it's a sliding scale. Is it like bromide or iodide, or is it harder? And I would say it's a lot harder. Still, hydride H minus is relatively small. And there's really not a lot to polarize it. It will depend a little bit where the hydride sticks to. We will see some reducing reagents when we talk about carbonyl compounds, and we will see that there's a difference between sodium hydride and lithium aluminum hydride. But if you think about sodium hydride, it's not a nucleophile at all. Right? So I would still think hydride is clearly here in this domain. Might not be as hard as fluoride, but it's clearly hard. We talked about already all the briefly Grignard reagents, and also along this line go alkyl lithium. Butyl lithium is a very common base which you use in organic chemistry. Again, we will see this a lot when we will talk about carbonyl compounds. Extremely hard. It's basically the equivalent of an butyl anion, or if you would like to write it like this, it's more an ionic compound. So usually when you have large electronegative differences here, then it's usually hard. So let me put something up here as well. So compounds which have a more ionic character are usually hard. And that is also why sodium hydride goes there. This is really more an ionic compound. Compounds which are more covalent composed are softer. And so if you do the direct comparison between organometallic compounds, and here you might have heard so far only about Grignard reagents, but if you go to or what am I doing here? That's of course not acids, right? That's of course also bases. So I put this on the wrong. You guys have this all right in your notes, right? Because nobody said something, right? So of course, if you look at the anion here, this is of course the base. If I want to look at the cation, I can save myself and can say, well, you know, I really meant the cation here. But since we are organic chemists, we have to put them, of course, if we talk about Let's put it in yellow what we mean. So if you have butyl lithium, so this should be in white then. Or let's say, not good with the colors here. Let's say methyl magnesium bromide, classical Grignard. This should be the methyl and the butyl. This should be a hard base. And then here, of course, on the other hand, lithium, magnesium, this should be quite hard acids. And here, on the other hand, if you go then in the periodic table to the more transition metals where you have d electrons, you see already there's much more ways to polarize, to distribute electrons. So everything here on the transition metals let's say copper plus, palladium, silver. This is really on the soft side. And here we are, as a general distinction, look at the main group metals, which we would also make or classify as being hard. And then at the same token, if the transition metals are the soft acids, if you coordinate them to something, and you have not seen that, but of course there are analogous compounds to the alkyl lithium compounds, which are cuprates. And let me just put this here in bracket in dots, because later on you will learn that the structure I write here is not really the structure which is useful in organic chemistry. But again, let's look at this as an analogous structure where we have copper as +1. So again, here we have the polarization that the alkyl group would be in carbanion. But this indeed is a much softer carbanion than if you have lithium coordinated. So the same R group here, so the same, let's say, methyl group, depending on the countercation, can be hard or soft. And this makes a great influence in reactivity. So let's look at this here for a moment more. What we need, because we want to look at alkyl halides, that's what we are doing that's what we are doing here. So an alkyl halide, the electronegativity difference between carbon and bromine is not so severe. And again, bromine being soft, so also the alkyl halide, which we now look in the polarizability delta plus, delta minus. So the R group really works as an electrophile, like an acid. This is really relatively soft. But at the same time, we talked about carbonyl groups. And this center here, because it has strongly electronegative substituents attached, this is really more a hard center here. And again, sliding scale, but as a general idea. So then what did we look at? We looked at the question, will an alkyl halide undergo a nucleophilic substitution with the Grignard reagent to form such a coupling product. And we would argue that this here is a soft acid. We will argue that this is a hard base. So we have a soft-hard combination here, which is not good. And so we do not see really reaction here. We look at the same reaction, or not at the same reaction, but at the same substrate, alkyl halide, reacting with sodium cyanide. And now again here, interesting question, what should be sodium cyanide? It's relatively small again, it is charged. On the other hand, it has a pi system. It's polarizable, the negative charge, or it's through the pi system relatively polarizable. So the whole entity is comparably soft. And then if you have actually two types of atoms here which can be act as a nucleophile, you can also distinguish between the two. And what do you think? Is the carbon the softer, or is carbon softer, or is the nitrogen softer? Yeah? Why is nitrogen softer? So one suggestion is nitrogen is softer. If I talk about polarizability, and then I will take again as an argument electronegativity, is that a good idea then? Think about this. Nitrogen is more electronegative than carbon. So nitrogen wants to keep the electrons to itself. It does not want to share. Carbon really wants probably to share a little bit easier. So usually, again here, you see we have more rule of thumbs here. So ionic, and let's say here more electronegative elements. This goes along with polarizability, because the more electronegative an element is, the less willing it is to share its electron, and the less polarizable it is. And so here we have less electronegative elements. So if I do a comparison here, I would argue that the cyanide really is hard. Or at least if I compare it to this. If I compare it to the Grignard reagent, I would clearly say the cyanide is not as hard as a Grignard reagent where we have, let me again fill this with live, like methyl magnesium bromide. I would say the methyl group is much harder than the cyanide, because the cyanide is more polarizable because it has a relatively large pi system here where it can polarize this. So if I would compare these two carbons, I would say this is softer than this. But if I compare this within the cyanide ion, I would argue that I would argue that the carbon is softer than the nitrogen here, simply based on electronegativity. Now you had this all, because I heard this all, and I put this all wrong on here. You had this all right in your script already, right? Because you just wanted to see if I realize my own mistake, or otherwise speak up, right? Say something. Otherwise, I have to do too much editing in the videos to get out the mistakes. Okay, so I would argue that this is soft on that carbon. And so when in doubt, when it reacts here, I would argue that the soft-soft combination is probably this one here, which leads really only 2 minutes, which leads to this combination. Now, why is it changing if we treat this with sodium cyanide, silver cyanide? Would anyone like to put some arguments forward here? How would you argue this, or try to argue this? Well, one thing could be, we have not really looked at the carbocation, the cation here. The sodium should be also, of course, be hard. And somewhere it has to be, right? So if the sodium here is coordinated with the cyanide ion, it's probably coordinated on nitrogen, because it wants to look for the hard partner. So it might coordinate the nitrogen, and the carbon can undergo the reaction. With the silver, it might be the other way around. The silver plus is more soft. It might be coordinated on the carbon, and so the nitrogen is available for the reaction, which will make in the end an isonitrile. But there's a second argument you could bring here. Silver and bromide is usually a very good match, right? You did already your inorganic practicum. Is that still that if you want to know if you have bromide in your solution in an analysis, in an inorganic analysis, you put silver nitride in there. If something crushes out, it's a silver halide. Do you do this? See, so everyone should know this. So silver and bromides really try to react easily with each other. And so this is, of course, also going on here. So in the presence of the silver cyanide, what is most likely occurring is that you create something like somewhere you abstract the bromide, you create a carbocation and your cyanide ion. And how do you think the hardness of your alkyl residue is changing from being in a bromide? So this would be more, if the cyanide reacts, this would be more an SN2 pathway. If you have silver in there, which might abstract first the bromide very readily and form a more ionic intermediate, so this might be more an SN1 pathway. And how do you think this is changing here? Is this harder, this cation, than the alkyl bromide? Absolutely. It's charged, it's ionic. So if I would compare these two, if I have to make a comparison between these two R's, then I would say as long as the bromide is coordinated to this, that's probably softer. If it is a naked carbocation, it's probably harder. And so with this, I would here understand now that I have probably formed the hard-hard combination by basically making the silver bromide. And look at this here. Why is silver and bromide such a good match? Again, you can explain this because you bring together two more or less soft acids and bases, right? Silver plus being a soft acid, bromide minus being a soft base. So they have a strong attraction to each other. And you all know this from the inorganic lab class. Silver bromide readily precipitates because it just forms a very stable bond. Okay, so keep this in mind, because you can explain with this soft, hard concept many, many things and can apply this in many different contexts. We will do this throughout the lecture, so keep this in mind. Wish you a very good weekend.